Work. We went to the moon. We landed human beings on the surface of another world. We brought them home safe, and we did it 6 times. So Mars, that is just the next step, right? Same basic idea. Work. Just a little farther away, a little more fuel, a little longer trip. We did the hard part already. Mars is just further down the same road. That assumption is completely wrong. Work. And I am going to show you exactly why the moon and Mars are not the same problem at different scales. They are fundamentally different problems. Work. And the difference is not the kind of thing you fix by building a slightly bigger rocket. The difference is mathematical. It lives inside an equation, and that equation is merciless. Getting to Mars is hard. Work. Landing on Mars is really hard. But getting off Mars and coming home, that is a different kind of hard. That is the kind of hard where nature looks you in the eye and says no. Work. And you have to figure out whether it really means it. Most public conversations about Mars stop at the landing, the renders of sleek habitats, the smiling astronauts in clean suits, the flag in the red dust. Work. The triumphant press conference, nobody talks about what happens next. Nobody talks about the moment the crew looks at each other. On a barren, frozen, nearly airless world, 55 million kilometers from the nearest machine shop, and asks the only question that actually matters: how do we get home? Before I walk you through the physics of why that question is so much harder than it sounds, I want you to hear from someone who has spent her career at the exact boundary where human ambition meets the unforgiving arithmetic of the universe. Let us start with what a rocket actually does. A rocket works by throwing mass out the back. That is it. You throw mass in one direction, and by Newton's third law, the rocket goes the other direction. Every rocket that has ever flown, from the first liquid-fueled test vehicles of the 1920s to the most advanced launch systems flying today, works on this one idea: Sybil. But there is a devastating catch. The fuel you are going to burn later, you have to carry now. And carrying it now means your rocket is heavier now, which means you need more fuel to accelerate all that fuel. Which means the rocket is heavier still, which means you need even more fuel. It is a vicious, unforgiving, self-reinforcing spiral. And there is an equation that captures this spiral with perfect mathematical brutality, the Tsiolkovsky rocket equation. The change in velocity you can achieve, your delta V equals the exhaust velocity of your engine times the natural logarithm of the ratio of your full mass to your empty mass. Delta V, VE times LM, 0 NAMF. If you have never dealt with logarithms, here is what this means in plain language. The relationship between speed and fuel is not linear, it is exponential. Going from 3 kilometers per second to 6 kilometers per second does not double your fuel requirement. It triples your mass ratio. At 9 kilometers per second, your rocket is 95% fuel by mass. Engineers call this the tyranny of the rocket equation, and it is tyranny in the most literal sense, an absolute, unappealable authority that every rocket designer has ever had to submit to. Consider the Saturn V, that magnificent machine, the most powerful rocket ever flown, weighed approximately 6.5 million pounds at launch. The part that actually went to the moon and came home, the command module, the astronauts, their equipment, weighed less than 1% of the total, less than 1%. Everything else was fuel. And tanks to hold the fuel, and engines to burn the fuel. The entire design philosophy of the Saturn V was a single obsessive idea. Got rid of mass as fast as possible. Use it. Dump it. Move on lighter. Stage by stage, the equation forced that design. The equation forces every design. And for Mars, the equation is about to show you something that nobody in the public conversation is saying clearly enough. Let us talk about the moon mission first, because understanding exactly what Apollo did is the only way to understand exactly how different Mars actually is. The delta V to get from Earth's surface into low Earth orbit is about 9.5 kilometers per second. From low Earth orbit to the moon and back, the additional delta V is roughly another 6 kilometers per second. The lunar module was extraordinarily light because the moon's gravity is weak, and the moon has no atmosphere, no heat shield needed for landing, no rockets needed for most of the descent. They left half the vehicle behind on the surface. Every single decision was ruthlessly focused on saving mass. And it worked. The total delta V budget for Apollo was roughly 15 to 16 kilometers per second. The Saturn V, the most powerful machine human beings have ever built, could just barely do it. Now, Mars, the first thing to understand is how far away it really is. The moon is about 3 days away. If something goes wrong, you can turn around. Apollo 13 proved that Mars is not 3 days away. At its closest approach, it is about 55 million kilometers. You have to launch at precisely the right time, follow a curved trajectory through interplanetary space, and arrive approximately 8 or 9 months later. 8 or 9 months in deep space with no possibility of turning around, no abort option, no safe harbor between here and there. If something goes wrong, you are in a metal tube hurtling through the void, and your only options are to fix it yourself or die. The nearest human being not on your spacecraft is getting farther away every single day. Now let us talk delta V for Mars, from low Earth orbit to a transfer trajectory toward Mars, about 3. 6 kilometers per second, slowing down when you arrive, another 1 to 2 kilometers per second to enter Mars orbit, then descending to the surface. And this is where Mars starts to show its teeth. Mars has an atmosphere, but it is a terrible atmosphere. About 1% the density of Earth's. Standing on the surface of Mars is like standing 35 kilometers above Earth. Thick enough that you need a heat shield during entry. Far too thin to stop you with a parachute alone. A parachute can only slow you to about 200 kilometers per hour. That is a crashing speed. So after your heat shield and parachute do their job, you have to fire rockets for the final deceleration. For a small robotic lander, this is manageable. NASA has done it. For a human mission needing to land 20 to 40 metric tons of crew, habitat, and equipment, it is a nightmare. The parachute approach does not scale. You would need a parachute hundreds of meters across. Which means rockets for most of the deceleration. And every kilogram of rocket fuel you bring for landing is a kilogram you had to carry all the way from Earth. NASA estimates that for every 1 metric ton you want on the surface of Mars, you need about 20 metric tons in low Earth orbit, 20 to 1. That ratio should give you nightmares. But let us suppose by some magnificent effort we solve all of that. Let us suppose we land a crew on Mars with everything they need. They do their science. They plant their flag. They document everything. Now they want to come home, and this is where the universe laughs, because getting off Mars is in many ways harder than getting to Mars. Not because Mars has stronger gravity. It does not. Mars has about 38% of Earth's gravity. The escape velocity is only 5 kilometers per second compared to 11.2 for Earth. That sounds manageable, but you are not launching from a well-equipped facility on Earth. You are launching from a barren, frozen, nearly airless world, 55 million kilometers from the nearest machine shop with whatever you brought and nothing else. Here are the numbers. To get off Mars and head home costs about 6 to 7 kilometers per second of delta V. With a good engine, your rocket at launch from Mars needs to be roughly 80% fuel by mass. That is 35 metric tons of fuel. For a 10 metric ton vehicle, 35 metric tons of rocket fuel on Mars where there is no fuel, and every single kilogram had to come from Earth. Now apply the rocket equation backwards. That 35 metric tons of fuel on Mars had to be launched from Earth, which means it needed fuel to get off Earth, which needed fuel to carry that fuel, which was then transferred to the Mars-bound spacecraft, which burned fuel to get to Mars, which burned fuel to slow down at Mars, which burned fuel to land on Mars, work, and now must be stored, perfectly preserved, in cryogenic tanks, on a planet where temperatures drop to minus 125 degrees Celsius, where dust storms can last months, where there is no maintenance crew for a year and a half until the launch window opens. Work. The cascade of mass through the rocket equation is catastrophic. You need fuel to carry the fuel, fuel to land the fuel, fuel to launch the fuel from Earth. Work. By the time you trace it all back, the total mass required is not just impractical, it borders on impossible with current technology. And now consider the timeline. The planets do not wait for you. Work. Earth and Mars align for a transfer orbit only every 26 months. If you land on Mars, you cannot leave whenever you want. You have to wait for the next launch window. Work. The most efficient mission profile requires staying on the surface for roughly 500 days. The entire round trip takes approximately 2.5 to 3 years. The long stay is not a choice. Work. It is a consequence of orbital mechanics. Work. And during those 500 days, the crew is living in a habitat the size of a couple of shipping containers, isolated by millions of kilometers, with a communication delay measured in minutes, exposed to cosmic radiation with no protective magnetosphere, with no hospital, no evacuation, no rescue, knowing that if anything goes seriously wrong, there is no one coming. Work. If something breaks, you fix it yourself. If someone gets sick, the crew manages it alone. If the habitat is compromised, you solve it with what you brought. Work. Because the nearest resupply is 9 months away, and you cannot even send it unless the launch window is open. This is why some very serious people have proposed a different approach. Work. Instead of bringing all the return fuel from Earth, make it on Mars. This is called in situ resource utilization. The concept is elegant. Mars's atmosphere is 95% carbon dioxide. Work. Crack that, and you have oxygen, diene water, ice beneath the surface. Split it into hydrogen and oxygen. Combine the hydrogen with carbon dioxide, and you can produce methane. Work. Methane and liquid oxygen are a perfectly functional rocket propellant. On paper, this is brilliant. Work. Instead of launching 35 metric tons of fuel from Earth, you ship a processing plant weighing 1 or 2 metric tons. Let it run autonomously for a year, and slowly fill your return tanks with locally produced propellant. Work. The rocket equation becomes far more forgiving because you have broken the chain, the mass multipliers collapse. The mission becomes, at least mathematically, feasible. But here is the problem. Work. Making fuel on Mars is something we have never done, not once, not even a small demonstration at meaningful scale. The chemistry is well understood in a laboratory. Work. But going from a laboratory demonstration to 35 metric tons of methane and liquid oxygen on the surface of Mars requires scaling up by a factor of millions. Work. It requires a chemical plant operating completely autonomously in a hostile environment at temperatures that drop to minus 125 degrees Celsius, with fine perchlorate dust that penetrates everything, with no human maintenance for a year or more. Work. And it has to work perfectly, because if it does not, your crew arrives to find empty tanks and no way home. Work. The recent MOXIE experiment on the Perseverance rover was the first demonstration of oxygen production on Mars. It produced approximately 10 grams of oxygen per hour. Work. You need roughly 7 metric tons of liquid oxygen for the return trip. MOX ran in short bursts, scaled up continuously with 0 failures over a full year. You begin to approach the requirement. Work. But begin to approach is not the same as solved. And even if you solve the fuel problem, you still have to solve everything else. The landing, the life support, the radiation, the psychology, the 500-day stay. Work. The 9-month voyages in both directions. The Earth re-entry at 12 kilometers per second, faster than any human has ever come home before. Each one of these is a monumental problem on its own. Work. Combined, they create a tapestry of difficulty that makes Apollo look like a weekend camping trip. And I mean that precisely not as exaggeration. Work. The total delta V for a moon round trip was approximately 15 to 16 kilometers per second. The total delta V for a Mars round trip is approximately 18 to 22 kilometers per second. Work. That sounds like a small difference. Only a few kilometers per second more, but the rocket equation does not care about your intuition. Work. Going from 15 to 20 kilometers per second can mean tripling or quadrupling the initial mass of the rocket. Work. A Mars mission might require a spacecraft assembled in orbit, weighing tens of thousands of metric tons. Nobody has ever built anything remotely close to that. I am not saying it is impossible. Work. I am saying it is hard in a way that the public conversation has not been honest about. It is not a matter of building a bigger rocket. It is not a matter of waiting for technology to improve a little. Work. It requires fundamental breakthroughs in multiple fields simultaneously, under conditions that have never been tested, with consequences for failure that are final. The moon was a challenge. Work. Mars is a crucible. The rocket equation ensures that every decision, every kilogram, every assumption is amplified into something enormous. It forces you to either bring everything or make everything work. And both options push hard against the limits of what we currently know how to do. That is the Mars return problem. It is not a problem of going there. It is a problem of coming back. Work. And coming back is where the universe shows you just how serious it is about keeping us here.